Hi everyone, we are Team YOLO. This is our project. It is an application of convolutional neural networks to determine vehicle types in a roadway image. Uh, in the slide, you can see the folks who are in our team. Our project in particular will be focusing on comparing two convolutional neural network architectures, one that we built from scratch and one of the ResNet 50. The input will be an image in a dataset, and the output will be the predicted label for the vehicle type in that image. You can see an example of in the current slide right now in front of you. For example, sedan, the image will be identified as sedan. Given the rise of artificial intelligence, novel applications of this technology are popping up everywhere. For example, car classification. It is of crucial importance for public safety in that it directly influences traffic monitoring, management, and control. It can also be potentially used for marketing purposes in addition to user clinics. These are one of the few examples of how this technology can be leveraged.
So for further progressing on our project, we did some research using the research paper available on internet. So the first research paper we researched or saw is about car classification using neural networks, in which CNN were used. CNN are a state-of-art neural network architecture that are primarily used for computer vision tasks. CNN can be applied in a number of different tasks such as image recognition, object location, and change detection. So for in this project, we saw that neural networks were used to classify 196 different brands of car, and for the type 2, which is car type recognition with deep neural networks, in this two data driven framework were used, that is deep neural network and support vector mechanism. At the After applying the methodology, we found out that deep neural network were giving the better accuracy. So this is the dataset specification used. The four classification of vehicles are sedan, SUV, truck, and van. For training purposes, we used 6,248 images. For validation, we used 2,011 images, and for testing, we used 20 images of each class, which are total 80 images.
During development of our deep learning model, we had few technical challenges. For the vehicle classification model, we required data for training, testing, and validating our self-developed model. Initially, we collected images from San Fernando and Ninth and Santa Clara and Ninth. There were a total of 50 images in each class, and the total images were 200 in number. So the initial split was 70%, that is 140 images for training, 20% that is 40 images for validation, 10% that is 20 images for testing. We trained the developed model with this data, but then the model was overfitting for any combination of parameters. By further evaluating this overfitting, we came across few reasons why this overfitting was happening. The one was the data set was small because we only had 200 data set, and then the image quality is very high because the pixel size is larger, and then the model was training based on background for any condition. This was due to the images were only taken in two locations, and then the backgrounds were similar to everything. So the solutions for this drawbacks was one was data annotation. It is the process of labeling or classifying any image using annotation tools. This will show the data features you want your model to recognize on its own. So this process will recognize the car, and you have to select the car in an image manually, and then you have to name the selected image as car. And then this was a very time consuming process. Later, we looked out for vehicle datasets, that is from on Kangol. We found dataset which had trucks, vans, SUV, and sedan. So we found a total of 8,089 images. For this project, we had two models. As you can see in figure 3, that was a self-developed model which we developed, which has an architecture which is optimal for image classification. We had two options for optimizer. One was RMS prop and Adam. After a lot of research, Adam optimizer was the best for image classification. So for a convolution neural network, the layers are in four. So one is convolutional layer, pooling layer, fully connected layer, classification layer. So the figure 4 represents the ResNet 50 model, which is already pre-trained network for about 100,000 images. So we change the top and bottom layer of the model to detect four classes. The figure 5 shows the vehicle classifier architecture, which has the image input of any class. Then it is processed into convolution layer 1 and convolution layer 2, then a pooling layer, and then a fully connected layer. The last layer is a softmax layer, which has four classes, which can predict the probability of the class.
The team generated two plots for better data visualization. As you can see on the plot on the left side is the loss versus epoch. The one on the right side is the accuracy versus epoch. And for the self-developed model, um, the training loss comes down from zero point 0.9 to zero point 0.1, and the validation loss comes down from zero point 0.7 to 0.25. As you can see, the validation loss is curve is higher than the loss curve. So our model is still a little bit overfitting. And in terms of the accuracy here, both validation and training accuracy goes up to around 95%, and it started stable after a epoch. For the ResNet 50 model, on the left side it shows the loss versus epoch curve, and both training loss and validation loss converge nicely after two epochs to nearly zero. On the right hand side is the accuracy versus epoch. Both the training accuracy and validation accuracy converge to around 100% after three epochs. The figure on the right side is to show our testing process. Um, there is a array after each image here. From left to right is the probability for SUV, sedan, truck, and van. So the model prediction would take the highest probability and label the target. So as you can see here, the first image is labeled as sedan, the second one is labeled as van, and the rest two are labeled as trucks. And on the left side is the table to compare the self-developed model and the ResNet 50 model. The self-developed model takes much less time to train, but it does has much higher in loss, whether in training or validation. And the ResNet 50 has higher training accuracy, validation accuracy, and also testing accuracy. So in conclusion, we can say the ResNet 50 is a better model to detect vehicle type.
The scope of this project can be implemented in various applications based on image classifiers. Currently, we have additional attachments such as FASTags to adjust or classify the type of vehicles which is attached to it. Using deep learning, we can automate the classification of vehicles at all the toll gates and charge based on the type of vehicles without any additional attachments such as FASTag. So another application is using deep learning model to detect the type of vehicle which violates the traffic rules and send traffic violation ticket instantaneously based on the type of vehicle. This concludes our project and we hope you enjoyed it. Thank you.